Okay, well, let's give a brief introduction of how to graph things in polar coordinates. So it works very differently from XY graphing. What you want to consider is you're going to be on concentric circles of different radii. Now, obviously, you could have a radius of like 1.5 or different values, but for most of the problems we'll just keep it at a radius, which is a whole number. Okay, so let's look at these problems very carefully. Okay, so this first one means we're going to be on a circle of radius 3. So I already have that drawn. And then what I'm going to do is turn an angle of 5 pi over 6. Okay, so that's going to put me approximately right there. Okay, so that's going to be point A. Again, I'm on the circle of radius 3, and I turned an angle of 5 pi over 6. Okay, so that one's good. Let's do the next point. The next point, a circle of radius 3, but now we're turning an angle of negative 7 pi over 6. So if you think about the negative angle, whoop, that's going to get me that exact same place. How about that? Okay, so now you see that there's something interesting about polar coordinates, that every point might have several ways to get to it. Okay, unlike XY graphing, which is kind of unique. Okay, so let's look at this one. Okay, 17 pi over 6. So the realization to make is that 17 pi over 6 is equal to 12 pi over 6, which is just 2 pi, plus an extra 5 pi over 6. So basically this does some extra rotation, if you think about it. So it does, you know, that's like a full circle, right? 12 pi over 6 is just 2 pi, so it does a full circle, and then it does an extra 5 pi over 6. So it does a full circle, and then does an extra 5 pi over 6. If you think about that, that's just going to be more rotating, but it's going to just get me still to that very same place. So that same point is represented by all of these, which is interesting. Okay, so let's try this one. Now, the thing, these all had positive radii. If I change it to a negative radius, let's see what's going to happen. Okay, first of all, let's consider for a minute what happens if I have the positive radius, which would be like A, okay? So if I did positive radius like this, positive 3 pi over 6, I'd be there. Now, what happens with a negative radius is it does a 180-degree flip. And the way you can think about that is you can make like a number line, okay? And so the number line, we'll make it go through the origin as it should. Okay, so it's like 3, 2, 1, 0, negative 1, negative 2, negative 3. So you can kind of think of like the radius as being on a number line, if that helps. Okay, so basically what this does compared to this is it's a 180-degree flip. Okay, so again, what I do, turn like as if I had the positive radius, 3 comma 5 pi over 6, except for the negative 3 is going to flip it over here. Okay, so that's going to be point D. Okay, that one's obviously different. Okay, so let's see if we can do this last one. Okay, so the way I do it, again, turn like you would for if it were a positive radius. Okay, so if I turn negative pi over 6, it's going to turn me here. That will be on a radius of 3. Okay, but this time, basically the numbers have to flip, right? So it's going to, the last thing I'm going to do with the negative is make it flip up there. Okay, so it turns out that A, B, C, and E are all going to be the same point, and D is the only one that's different. Okay, so the general gist is if you're graphing like R, theta, okay, you just treat theta as you normally treat it from standard position, and you're working on a circle of radius R. Okay, so the problem is if you have like a negative value for R, okay, basically what these things are going to be is they're going to be sort of 180-degree rotations of one another. So again, if you want to graph this, okay, in order to graph this, you want to instead graph that temporarily and then do a 180-degree rotation on it to get that. So basically that negative R, basically all it does is does a negative 180, or does a 180-degree rotation from what that one is. Okay, let's see if this formula works even when the sum is probably negative, or when the multiplier is negative, you know, when strange things happen, you might be like, is this formula really going to still work? But let's see that it does. Okay, so let's take the same series we had last time and make it alternating. So alternating, one way to do that is multiply by a negative ratio. So, okay, so we have times -5. Okay, if I take this thing times -5, then I get 100. 100 times -5, -500. So hopefully you see multiplying by -5 each time is going to make it alternating like that. Okay, so let's say I want to do the first 6 terms of this one. Okay, so here's how it would work. Okay, so S sub 6 would be, again, the first term, 1 minus the ratio to the 6 over 1 minus R. So it's similar to the last problem, except, you know, we get negative thing for the ratio. Okay, so again, you have to plug it in very carefully. The first term is 4. It's going to be 1 minus, now this is interesting because -5 to the 6 is the same as 5 to the 6, but you know, plug it in like this because it could have been the 7th power if we were adding up 7 things or something like that. So that's just kind of a cautious thing to do. Okay, and it's going to be divided by 1 minus the ratio. So it's going to be 1 minus -5, which of course is going to turn into, if you just want to plug it in the calculator, is dividing by 6. That makes sense to me. Okay, so anyway, plugging that into the calculator very carefully. Again, this is where most of the errors happen, is plugging it into the calculator. I end up with this sum of -10,416. Okay, so I did the same thing. You want to maybe just calculate them out real quick. You can type those into your calculator. You know, what quick inspection should tell you that there's more negative things in this sum than there are positive things, but they somewhat cancel each other out. But obviously that last negative thing is really swaying the value of the sequence. But anyway, adding those things up on the calculator individually, I got the same sum. So it works even with crazy situations where, you know, the sum is negative or you have a negative ratio. The formula should always work. Okay, so let's talk about how you would switch from polar coordinates to regular coordinates. So obviously with polar coordinates, what you're given is you're given an R and a theta, right? And then you want to transform them into a regular X and a regular Y. Okay, so here's how it's going to basically work. Okay, so you turn, in a normal like unit circle, you turn theta, okay? And then this would be considered sine of theta, right? And this would be considered cosine of theta. And hopefully you just kind of remember those from our setup in the unit circle. So if you scale those, right? So polar coordinate graphing is just going to involve, you know, still turning an angle theta, but now you can be on any radius of circle, okay? So your x coordinate that you're going to get up to here, okay? So this would be considered your r theta, okay? But if you want to put it in regular coordinates, it's just going to be r cosine theta for the x, okay? And then it's going to be r sine theta for the y. And hopefully you see that all that was doing is it's just taking this drawing here and scaling up by r. So the 1 of radius becomes an r, and then, you know, this side gets multiplied by r, this side gets multiplied by r. So these are really pretty straightforward. They just kind of come from the basic trigonometry. So you can translate any point that's in a polar form into a coordinate graphing form pretty easily. Okay, so let's look at this point. It's 3 for the radius and pi over 3 for the angle. Okay, so let's draw a picture of that. Okay, so it'd be something like this, where you'd be on a circle of radius 3 and the angle would be pi over 3. So that would put you here for that coordinate. Okay, so obviously you could draw the circles and so forth. But this part's really straightforward and simple for finding the x and y coordinates for this one. Okay, so this would just be 3 cosine theta, right, from the last problem, and this would just be 3 sine theta from the last problem. So putting that in terms of the exact thing that we have, it'd be 3 cosine of pi over 3. Okay, so hopefully you could do that one pretty quickly. So the cosine of pi over 3 is just a half, right? Okay, so that's just going to be 3 halves. And then for this one, the sine of pi over 3 is going to be root 3 over 2, right? So it'd be 3 times root 3 over 2. So it'd be, that's going to be 3 root 3 over 2. Okay, so if I want to, again, transfer that, it's just going to be, the x part is just going to be 3 halves, right? And then the y part is going to be 3 root 3 over 2. Okay, so what this allows for in graphing is that you can do some pretty amazing and interesting things that you can't really do as easily with XY coordinates, because the way this works is basically what you have is you can make functions such that the radius is now a function of the angle turned, okay? So if you think about it, you can make it so if you turn a little bit of an angle, you know, you have a little bit of a radius. And then you can make it so, oh, well, maybe you turn a little more and you have a bigger radius, okay? Let's say it does something like that. And then you turn a little, you know, you turn a little more, maybe your radius gets smaller again, okay? So, and maybe it goes back to the radius even being 0. So you can see maybe you can make, you know, some interesting designs. It's not done very well in this one, where you change the radius as the function of the angle that you turn. So what it does is it allows you to make all sorts of like symmetric things and all sorts of designs, all sorts of flowers, all sorts of things like that. So I'll show you some really interesting things you could do using this kind of graphing. Okay, to graph something in a polar mode, what you need to do is push the mode button. Okay, and so what you're going to see is function, parametric, and polar. You're going to want to switch it to polar. Okay, and then you could go to the y equals menu. Okay, so I'm just going to graph this equation. Actually, let me do the second one. Okay, so graphing that, let's see what it looks like. Okay, so that was pretty amazing. Obviously there's some setup that you have to get for the window. I just did a window that was like -10 to 10, I think, on each side. And then the theta, I think I did, you want to do at least a full circle. So I think I did a little bit more. So I just did, 10 instead of 6.28 for that one. But anyway, I think you can see that certain things are much easier to graph in polar coordinates, such as flowers, things like that. So for Mother's Day, I thought you could show your mom a flower if you were interested. If not, that's okay. Okay, so let's think about what's going to happen with this function. So it's just r equals theta. So what's going to happen is theta is going to get bigger and bigger, okay? And the radius is also going to get bigger as the angle I turn gets bigger. So think about what kind of graph that might create. Okay, so theta is getting bigger, the radius is getting bigger. Obviously that's going to continue on for as long as I keep on extending theta. Okay, let's summarize what we know about graphing with polar coordinates. Okay, so basically it's a new framework of graphing. And it's you're given the radius and the theta that you need to turn in order to do the graphing. Usually when you make functions with this though, theta is considered to be the input and the radius depends on the angle that you turn. Okay, so going from polar to rectangular, what you want to just do is x is going to be r cosine theta and y is going to be r sine theta. Okay, it turns out some graphs are really easy to draw in polar coordinates. Let me give you two examples of two easy things to draw. So if I want to draw a circle of radius 2, all I have to do is let r equal 2. And my circle is drawn. Okay, so really easy to draw circles in polar coordinates. The other thing that's easy to draw is lines at a slant. Okay, so if I want to, for instance, draw theta equals pi over 6, it's really easy. I just turn pi over 6, okay? And that's my line. Okay, so obviously it's assumed r can be anything. Just like when you graph x equals 4, y can be anything. So if theta equals pi over 6, r can be anything. Obviously, the other things that are really straightforward to draw with polar coordinates are things like flowers, okay? So those often take the form of something like r equals, here you want to put in some kind of scaling number, and then you could do cosine, and then here you want to do another scaling number, okay? So you could put different numbers in here. I think I put like 7 in and 5 in, but you could put in different numbers for those things. So those are going to graph flowers. And then if you do just r equals theta, obviously you can modify this to be r equals 2 theta, or, you know, you could experiment with that or whatever. So if r equals theta is just going to draw a spiral going outward, okay? You can think of what happens if you draw r equals negative theta. Maybe you draw the spiral the other way. All right, so I'll let you play with that.